So first of all, what is feature engineering? Well, for those of you who aren't necessarily familiar with it, feature engineering is both an art as well as a science of transforming raw data into valuable attributes for a prediction model. And this is a very crucial step in machine learning because even with the same algorithms, by using certain features, you might get better ways to get to your end results. However, there is no one feature to rule them all, even though some might dramatically improve your performance. And we like to think of these features as being families of features. So if we can think about these families of features like a battleships game. So you're trying to figure out what's the best way of predicting whatever you're trying to predict, and you found something. So you hit one part of your battleship. That's your family of features. So from there, it's pretty hard to figure out what else there is in that family. And this is how you sink part of your opponent's fleet. And it's pretty much the same in machine learning. So how do we actually go about creating new features when we move on from project to project? Well, first of all, we take a step back and we think about all the previous projects that we've actually worked on. And we actually end up seeing that there's really two main ways of doing this. Usually it's a lot of statistical operations, but also some domain knowledge. Initially, when we approach a project, we don't really know much about the project itself. We try to find out some information, but we might see some resistance from stakeholders. So we find a way to summarize the information that we are given. But as this project evolves, we learn more and more about the project, what we're trying to tackle, stakeholders, users, etc. So we start getting a better understanding of the data, and thus we can move on and create better features. So what do I actually mean by that? So what happens tends to be the following. While we go through the process of gaining domain knowledge, we start to see that the amount of features that we end up using is inversely proportionate. So while initially we build a whole bunch of features using statistical approaches, while we start getting more information about the project, our features actually narrow down to what we believe is more specific. However, we can still get a lot of information just by using a brute force approach, but still thinking about domain knowledge. So we're trying to figure out how do we introduce domain knowledge in our brute force approach of creating statistical features. Okay, so what is the motivation to actually do this? Well, we at Dataiku, we're working with a lot of different companies from a lot of different industries, and we tend to see people kind of facing the same issues, whether they're on the business side, or on the engineering side, or they're on the use case side. A lot of our clients are dealing with churn, so they're interested in how to best approach churn. And we look at these use cases as vertical projects. And when we look at them individually, they seem to be very, very different. Some might be tackling churn internally. Some might be tackling churn for external purposes. But in the end, the differences in data are not that big. But they're quite unique in the sense of domain knowledge. But you can still try and see that there's things which are common to all projects. It would be the same in a fraud detection case, because usually you tend to find transactional data, for example. So there's always some sort of structure in the data that we want to explore. And especially in the use cases that I previously mentioned, we can see two common factors. There's a notion of time, and there's also a notion of events. So the goal of feature engineering in those types of cases is how do we actually join the notion of time with the notion of events, but also leverage the high-level information that we get from the business stakeholders. Normally, we would go about and generate features one by one. But is there any way to actually automate this to make this slightly better? What I actually mean is, how do we get over the really boring part of making features? So my colleague Yu did a very, very scientific survey where he looked at how long feature engineering takes and if it's really fun. And he found out that it's not really fun, at least not for him. So because he wanted to find a way on how to change this boring and repetitive project, because he was working with a lot of customers, but in the end he noticed that he was using a lot of the same features. So that's when the internal discussion started around this. Also, everybody else in the data science domain tends to do automatic feature engineering through diverse ways. Some might be doing it through deep learning, but that's not what we're going to talk about today. So let's look at a few examples of how this data sharing knowledge actually occurs. So Airbnb, for example, they have an internal tool called Zipline. What happens within Airbnb is all their different data scientists, whenever they query their databases to create features, they save all these queries in an internal repository. So everybody else has access to high quality vetted ways of doing feature generation. Another example is a company called Stitch Fix in the US. They decided to write their SQL templates using a tool called Jinja 2, which is a text template language that supports Flask or Django. And this leverages the flexible nature to update these queries automatically. And then there's also a different type of approach. So companies dealing with relational databases, one way to approach this is looking at graph dependencies and how tables link up together. It's basically a big join operation between tables, but at the same time, you also augment all the tables with newly created features, aggregated features. But in this way, you might end up with a feature that looks something like the sum of the mean of the sum of column X. A system like this does exist, so it's an open source Python package called Feature Tools, developed by the guys at Feature Lab. So something like this also exists. Just looking at the dependency graph and then doing all the computation in Python. So there are a few methods that exist out there. There are, of course, a lot more. But all the methods that I've been through right now try and deal with all types of data sets. So they consider themselves to be limitless. So we wanted to find something a bit more specific that we could actually showcase to our peers to make sure that they can use it in their day-to-day lives and they can immediately see how this would relate to them. So we started by reducing the scope of the problem to a very targeted type of data set. A data set with temporal dimensions, like the ones we can use for churn or fraud transactions. We also wanted to use general domain knowledge to set what the pertinent operations are. But we also wanted to focus on the interpretability of the system, because that's something which a lot of people require, and we think is quite necessary to understand how everything works. So this is how AutoFeat came into play. So what exactly is AutoFeat? So AutoFeat is a high-level Python framework that helps data scientists to generate expressive features for their particular problem with a very high-level understanding of the data as well as the use case itself. It basically does all the boring parts that you was talking about, but it still gives you control of what you actually generate. So you don't just generate a whole bunch of random features and then hope that your algorithm will just choose the best and work with them. So if you remember the graph I showed initially, our approach basically wants to automate the initial part of creating features with some domain knowledge. But we always want that domain knowledge to be there. So we want to rely on previous experience, but also facilitate the whole process. So I'm going to go a bit deeper into AutoFeat right now. I'm going to explain the framework for temporal data and the definition for temporal aggregations. and I'm going to present the building block of the package itself, the feature factory class. So the first building block is the temporal data model. So this basically allows us to see the big picture when we do feature engineering and approach it in a logical and reproducible way. So there's a few definitions to be made. So in our framework, we have a subject that we're looking at, which is basically an ensemble of columns that defines a smallest unit that we're interested in for our project, but also a state, which are some columns that describe where that subject is currently in. So what state is he in? And usually every row corresponds to an event or some sort of snapshot of a specific subject state at a specific moment in time. So let's think about a normal transactional database to illustrate some of these ideas. So usually each row is a client purchasing something, let's say a product. So the definition in this case, it would really depend on the use case. For a pure churn use case, the subject would be the client because we're interested in when the client will churn. But if we're looking at fraudulent transactions, the level then changes and it becomes more narrow. So we're looking at both the user as well as the timestamp of that particular event. Also, we have two goals while doing feature engineering for this type of model. The first goal is we want to summarize the information that we have available for a particular time window. So, for example, going back to our transactional data, how much did our client spend in the last 3 months? Or out of all the products that he bought, what's the percentage of groceries or percentage of clothes that she bought? But we also want to understand the evolution of our subject through time. This is information around frequency of events as well as recency of events. So, for example, how many times did the client purchase something in the last 6 months? Or when was their last purchase made? So it's things like that we're trying to tackle. So remember I was talking about families of features, so our battleships. So we've looked at several battleships that we thought we could find. First one is frequency. So how often does a client do a specific action? The second one is recency. So when did our client last buy something? Also this is a more specific battleship, so something that might be slightly smaller and harder to find. But what is their spending habits? So things like, do they always purchase a full dollar amount? Do they spend 5 cents in every transaction, etc.? But they're also looking at distributions. So basically percentage values of categorical columns. So how many events have happened on a Sunday? The second building block is temporal aggregation. So how do we take these feature families, but walk them and guide them through time? And there's two main ways in which we can do this. The first one is a fixed way. So this one-shot aggregation with a fixed timestamp tends to be more common in churn cases. That's actually a pretty good example when we know that the customer will stop using the product, and we want to find out, well, what was their whole historic activity over the past X days. But there's also another way, doing sequential aggregation with rolling timestamp. So for each subject, we aggregate features on a rolling period, so event by event. And there is no fixed reference date. There are just intervals which we would like to define using our own domain knowledge on the subject, on the topic. So how does the package itself actually work? Well, there's basically 3 phases. The first one is we define some SQL query templates. So even though it's a Python package, everything will also runs in database. So we define SQL query templates with placeholder variables, so things that we want to define at a later stage. So the name of our columns, our temporal conditions, etc. Then we populate the placeholders with our desired values. And then finally, we translate and execute the SQL scripts. And we also have optimization steps within. So for every feature family, we create a new script, but then that would result in a lot of different SQL tables. So there is optimization to join those tables as well. So let me go into a specific example. So this is the main class of the package. This is a classic fit transform API, where we basically scan the input data set and we store metadata about it. So in this case, we look at user ID. We define what our features would be because we don't always want to use all the features. So in this case, we're taking frequency, recency, and monetary features. We define our categorical and numerical columns. So basically, this scans the data set, and it does schema checks and quality checks, and then takes this and moves it forward to transform everything to the corresponding SQL dialect. So let's say we're trying to figure out the frequency of buying events in the last 6 months. So we have to define our window, which is 6 months. We have to define our primary key, in which case it's the user ID. And we also want to add an additional filter because we don't, let's say we have a table where you don't just have buy orders, we have sell orders as well. And we're only interested in buy orders. So the way this actually works is we have information about our metadata, the one that we're actually creating, so the red boxes. So our interval, our event type, which is our filter, and then our subject. And then we're automatically creating we're automatically generating features around frequency and mean frequency. So finally, a short conclusion. So feature engineering is quite important in day-to-day lives of data scientists for mainly 2 purposes. The first one is to increase the performance of predictive models. And the second one is to create some sort of expressive ways in which data scientists or data analysts or business stakeholders have a deeper understanding of the problem at heart. Most approaches so far for automatic feature engineering tend to tackle the former. They try to either brute force their way in, creating a whole bunch of different features and either throwing computation or computation or feature reduction mechanism to try and narrow down to the best features, but they still have to generate everything that's possible. The other way is to use deep learning and don't necessarily understand what the features that you are creating are, but just leading to better performance. And we wanted to go into a different direction because in a lot of real life use cases, this is not what actually happens. So I was actually talking to a data scientist in Cambridge the other day, and he was telling me how within their data science team they built a great way to figure out fraud for an online gaming platform that they have. And the model was working very well. The finance team agreed that their model is working very well, but they didn't understand it because they had no idea what was happening. So it got rejected from being put into production. What they instead did is create features based on decision trees, and then they used those features for rule-based approaches. So that was very, very interesting because that related a lot to what we're trying to do. We're trying to offer interpretability for those people who do have, in the end, domain knowledge, but making sure that they're more effective in how they do their projects. Thank you very much for your attention, and if you have any questions, I'm more than happy to try and answer them. Thank you.
Thanks, Silviu. Great talk. Any question?
Thanks, really interesting. So you talked about the feature engineering, and in terms of interpretability, what about evaluating the predictive power of the features that you are producing? Do you do that? How do you do that?
So no, the The framework itself is just for generating the features. The analyzing their capability is done at a later stage by whoever is doing the project itself. It's mainly a tool to help you not do things one by one, but do, well, basically brute force, but brute force with knowledge. So you know that you might have relevant events every 3 days, 3 weeks, and 3 months. So you want to automatically generate that rather than doing it one by one.
Good, and just following up, on the chat that you showed before showing the percentage, I think was...
This one?
No, the chart where you showed the percentage reduction in,
yes.
I think was the feature set
Yep.
size. So yeah, I guess in order to achieve that and reduce the number of features that you use, somehow you need to narrow it down to the most predictive ones. That's why I was
yes. So
getting to that. So
you're right. So initially, the way you climb up to the starting point is brute forcing, and then with domain knowledge, you start reducing some of those. But this gets you to this basically you start later down the line because you already gained some domain knowledge and the features are generated with your help.